Alright, welcome back. So today what we're going to be looking at is continuing our stoichiometry and looking specifically at gas stoichiometry. So our last one was on gravimetrics, so we are using the mass and molar mass equation. Now for gas stoichiometry, we are going to be using, of course, our gas laws. So these here, it's probably been a while since we actually looked at some of the gas stuff, so just values to remember. There is the STP values and SATP values. So remember, the temperature is 0 degrees Celsius for STP, pressure is 101.325 kilopascals, and the volume, or the molar volume, is 22.4 liters per mole. And for SATP, that's 25 degrees Celsius, 100 kilopascals, and the molar volume is 24.8 liters per mole. So also just a little reminder as well that when we are doing calculations using gas values, we need to convert everything into the Kelvin scale. So in order to get that, the temperature in Kelvin is just equal to the temperature in degrees Celsius plus 273.15, or just 273. Now, if you want to get temperature in degrees Celsius, we take temperature in degrees Kelvin and we subtract 273.15. That's just, of course, rearranging our equation right here. Now, other important equations that we will need to use, we have two equations to find the number of moles depending on information that you're given. We get number of moles equal to volume divided by the molar volume. Remember, molar volume is if you read STP or SATP. And if you're not given STP or SATP conditions, we find the number of moles by multiplying PV and dividing by R and T. And remember, R is the ideal gas constant found on the back of your periodic tables. P is pressure in kilopascals. V is volume, and it needs to be in liters. And of course, T is temperature, and it needs to be in kelvins, or Kelvin, sorry. So, for our procedure for solving gas stoichiometry problems, you'll notice that it is going to be the exact same as gravimetric. The only difference is our equations we're going to use to find the number of moles. So step number 2 is going to differ, and of course step number 4 is also going to differ depending on if it's asking to solve for volume, pressure, or temperature, or something like that. So as we see, our first step is write the complete balanced chemical equation for the reaction, and we can calculate the molar masses of appropriate substances. That is if the question is asking for either A, we're given a mass, or it's asking to solve for a mass. If the question does not have any masses or is not asking for a mass, you can omit this out. Step number 2 is we find the number of moles of our given substance using number of moles equals V over Vm, or number of moles peak V over RT, or number of moles is equal to mass over molar mass, because we can get a mixture of stoichiometries. Step number 3 is going to be the same. We determine the number of moles of our wanted substance, right, or required substance using our mole ratio. And remember, our mole ratio is just the coefficient of our wanted over our given, and we do this step right here. And then, of course, finally, last, solve the question using the appropriate equation. So it's basically you just have to read and ask for, what is it asking for volume? Is it asking for pressure? Is it asking for mass? So our 4 steps will be the same. So let's looking at our first question. We have if 275 grams of propane burns in a gas barbecue, what volume of oxygen measured at STP is required for that reaction? So of course, propane, normally if I'm giving you a hydrocarbon, I will tell you its chemical formula. But with this one right here, because I knew we were going to do this together, I never gave it to you. But propane is C3H8, and of course this is a gas. Plus, it is a hydrocarbon combustion reaction, so we're going to react with oxygen gas. And for all hydrocarbon combustion reactions, we produce CO2 gas and H2O gas. And of course, we do need to balance, so there's 3 carbons in propane, so we need 3 carbon dioxides. There's 8 hydrogens in propane, so we need 4 H2O. And what this creates then is 10 oxygens on our product side. So in order to get 10 oxygens, we stick a 5 in front of oxygen. Now, for this one right here, I'm not going to write in the molar masses because we're going to put those in when we actually need it. But because of reading the question, I know that propane is my given because we have 275 grams of propane burns, and it's asking for what volume of oxygen. And my oxygen is right here. This is my wanted. So I have my substances highlighted. Now step 2 is always finding the number of moles of our given substance. So because we are given 275 grams of propane, we go number of moles is equal to the mass divided by our molar mass. So we got 275 grams of propane divided by the molar mass. So we have 3 carbons and 8 hydrogens. So when we add all those together, we get 44.11 grams per mole, and this leaves us with 6.234414 moles of propane. Now, step 3 is always find the number of moles of our wanted, right? So that was our given, and that is number of moles are given times our mole ratio. So that's equal to our 6.234414 mole. Now our mole ratio, remember, is the coefficient of our wanted over the coefficient of our given. So our wanted right here is our oxygen, so the coefficient in front of that is 5, and our given is propane, the coefficient in front of that is 1. So that leaves us with 31.17207 moles. And finally, the last step is solve the question, and it's asking for what volume measured at STP. So of course for that we need to rearrange the equation of, I'm just going to write up here, the equation we had, N is equal to number of moles is equal to, V over Vm. So in order, of course, to rearrange and solve for volume, we need to multiply both sides by Vm. So V is equal to NV. And just because we know it's STP, just write N STP. So you got 31.17207 moles times, you can flip back to the previous page and figure out what the molar volume at STP is, or look at the back of your periodic tables, and we have 22.4 liters per mole, and we are left with 698 liters. And of course that's 3 significant digits, because we had 3 significant digits in our question right here. So that is using our stoichiometry to solve these questions. So you will notice that step 1, 2, and 3 were the same as what we done last week with the gravimetric. The only difference right here was our question 4, just because we used one of the molar volumes to kind of solve for this. But that's kind of the steps that we're going to be going with now, is that we're just going to be, step 2 and step 4 are just going to be different, and it all comes down to what moles are, or what equations are we using to get our number of moles for a given, and what equations are we using to solve. So let's look at our next one. So if you want, you can definitely pause the video and try to skip ahead a little bit to see if you get the right answer, but I'm just going to go over this one with you as well, and then of course just kind of give you an answer to 3 and see if you can get that, and then allow you to go into your workbooks and see if you can get those. So this right here, it says what mass of oxygen is used during the burning of methane to produce 15 liters of carbon dioxide and a pressure of 235 kilopascals at a temperature of 85 degrees Celsius. So now we can tell that this is not under STP or SATP conditions, so we will need to use our ideal gas law, and we do have what mass of oxygen. So we do have the burning of methane first, so our balanced chemical equation. So methane is CH4, is a gas. Of course, combustion reaction reacts with O2 gas, right? All combustion reactions need oxygen. And our products is carbon dioxide gas and, of course, water vapor. Now to balance, we need 1 carbon from our methane, so we keep the coefficient 1 in front of carbon dioxide. We need 4 hydrogens on our product side, so we multiply water by 2. and that creates 4 oxygen, so then our oxygen is also multiplied by 2 on the reactant side to balance. Now, also, just like before, what mass of oxygen, so obviously this is our wanted, is used for the burning of methane to produce 15 liters of carbon dioxide at a pressure of 235 kPa. So this is our given this time around. Now, even before we kind of jump right in, we do know with our ideal gas law, kilopascals is needed. Volume is in liters, also needed, but this we need to convert into Kelvin. So we add 273, and that gives us 358 Kelvin. So you can kind of scratch out that degrees Celsius if you want and kind of put in Kelvin, or if you want to write it down somewhere over on the other side, you can as well, right? As long as you realize that you need to convert that. So our next step, 2, is find the number of moles of our given. Now this one right here, because our given is carbon dioxide, we have pressure, we have volume, and we have temperature, we are going to have to use the ideal gas law. So that equation, rearranged properly for number of moles, is PV over RT. So our pressure is 235 kPa. Our volume was 15 liters. Our R value, back of the periodic table, 8.314 liters kilopascals over moles Kelvin. And our temperature was 358 Kelvin. So when we plug all this into our calculator, we should get 1.1843118 moles. Now you don't need to keep all those digits, but I just like to keep extra. Now our third step, number of moles of our wanted is equal to number of moles of our given times our mole ratio. Step 3 is always going to be the same, so number of moles are given, we just solve for. Sorry, I meant to actually write down the number there, not Ng. So we go 1.1843118 mole times our mole ratio. So remember, mole ratio is the coefficient of our wanted over the coefficient of our given. So our wanted is oxygen, the coefficient in front of that is 2. Our given is carbon dioxide, coefficient in front of that is 1. So we multiply the number of moles are given by 2 over 1, and we get an answer of 2.3686237 moles. And last but not least, once you get that one, we solve our question. So of course, our question is what mass of oxygen. So mass is just number of moles times our molar mass. So our number of moles we just solved, so that's 2.3686237 moles. And the molar mass for oxygen, it is O2, so that's 2 times the molar mass of oxygen in our periodic table. That gives us to 32.00 grams per mole. And our final answer with 2 significant digits because that 15 liters up here. And of course, even our degrees Celsius, only 2 significant digits. So our final answer is going to be 2 significant digits. And we get 76 grams. And that is the answer for number 2. So you'll notice a lot of these stoichiometry problems will be very samey after a while. It's just writing down the balanced chemical equation. Of course, you have to be careful about that. And of course, just determining, highlighting your wanted and given and knowing what formulas you need to use. So it'd be very handy to kind of have almost like a little cheat sheet with all the formulas, all of them rearranged, just kind of on a separate sheet of paper kind of close to your working, so you can just reference it as you're going through, because the more you use it, the easier it'll be to kind of remember all of them. And last but not least, example 3. So I'm going to let you guys kind of do this one on your own. And you're going to keep doing it until you get an answer of volume is equal to 37 liters. Of course, it's going to be 2 significant digits because of 2 of them has 2 significant digits up here. So I want you to read through this one on your own and try it until you get a volume of 37 liters. Now, if you want to see the workings for this one, of course, you can always look at the answer key that is posted up on Google Classroom. But definitely try this one several times. If you don't get it right the first time, just keep trying it until you get it. Generally for these here, if you're going to make a mistake, it's going to be in the balancing of your chemical equation. So always make sure you have your chemical equation correct. And of course balancing, and generally another thing that people tend to just mistake as well is that a molar mass calculation. So if you're unsure, just go back and review the molar mass. But anyway, see if you can get that, and of course if you can't get it and you still need some extra help, just let me know and we can set up a private Google Meet. But anyway, that is it for solution stoichiometry, so please try your CYU books, and I'll see you guys for your next one, which, oh sorry, that was gas stoichiometry. Your next one is going to be solution stoichiometry. So I'll see you guys for that one.